Good day, my name is Margina, and in this presentation, I will demonstrate my Java-based radiation counting simulation, which models the statistical nature of radiation detection using Poisson and Gaussian distribution. The simulation allowed users to explore how radiation counts fluctuate and how the Gaussian distribution emerged from the Poisson distribution at large mean value, in accordance with the central limit theorem also. Radiation detection is a random process because radioactive decays occurs independently and unpredictably. For a fixed time interval, the number of detected events follows a Poisson distribution, where the mu represents the mean number of counts and the n is the number of detected events. A key property of Poisson distribution is that its variance is equal to its mean. The statistical uncertainty, or the error, is the standard deviation, which equals to the square root of the mu. As the mu increases, the Poisson distribution becomes more symmetric and gradually approaches the Gaussian distribution. This transition is a direct consequence of the central limit theorem, and it forms the core concept explored in this simulation also. So now I will demonstrate the graphical user interface. First, the user inputs the mean count, mu, which controls the average number of radiation events per measurement. Next, the number of trials n determines the number of measurements simulated. As the increasing of the number of trials, it does not change the physics, but it improves the histogram statistical reliability. Then the user selects the distribution model, either Poisson or Gaussian. The statistical error will be calculated in right-hand side after we press the simulate button. Okay, so for the program, it also provides physics insight warning. When the user input a small mu and choosing a Gaussian, it will trigger a warning because Poisson statistic is more appropriate. Otherwise, for a large mu, such as 80, choose a Poisson. It also occurs a warning that reminds users that Gaussian approximation is valid and easy to use. Okay, so now I choose this one. And in this panel, it will across the maximum and minimum count observed, also the theoretical mean and variance for this situation. So we'll click the save. Go to the next one, we plot it. When simulate the button is pressed, the program generates random radiation counts based on selected distribution, and each trial produces one count value, and all results are stored in data panel. So the histogram represents a frequency of detected radiation counts over many trials, and each bar shows how often a particular count's value occurs. So now, if we try for a small mute, okay, just 3 with the Poisson, save it, plot it. In a small mute, the Poisson distribution is discrete and asymmetric, reflecting the rare and random nature of radiation events. As the mu increases, the histogram becomes more symmetric and closely matched to overlap Gaussian curve, demonstrating the validity of Gaussian approximation at large mean value, just like this one. So 100 maybe. Oh, sorry, this one we need to use this one. Okay. So this visually confirms the central limit theorem, showing how macroscopic statistical behavior emerges from microscopic random processes. This is why Gaussian statistics are widely used in radiation measurements at high count rates. So through this simulation, users can clearly observe how statistical fluctuation behave and how the Gaussian distribution emerge from Poisson statistic at large mean value. So that's all from me. Thank you.